survey two large and important topics where you'll find me, you'll find quite a few lectures of mine online, sometimes going into these in great detail. The first, but I want to give you a flavor of these at least, okay? The first of them is the topic of parameter variation, okay? And we're going to also use this to talk about stochastics within a model. So, ladies and gentlemen, I would like you to go and, from the AnyLogic Help menu, I would like you to open up an example model called SIR agent-based calibration, okay? SIR agent-based calibration. So I'll do it with you. Help, AnyLogic Help, and, oh man, sorry, what am I doing? Help example models is what I meant. Apologies. Example models. And you should get a set of example models. I'm going to make it full screen and, oh, I don't know why I went to this. I said example models. Well, okay, fine. That's interesting. Why is it on this particular? That's very strange. Yes, SIR agent-based calibration. Now, maybe TA help. So the example models. Oh, there they are. Okay, thank you. Yeah, the big fonts have changed it. Okay, SIR agent-based calibration. Okay, and this will load it in, but we need to put this out of full screen. Now it's funny, I can't see the. It's under all models to the right. Yeah. Could TAs help? Okay, who needs TA help finding that? You got it? Yeah. Okay. 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 So, ladies and gentlemen, we're going to look at this model in two different ways. We're going to first look at it for this issue of parameter variation, and secondly, from the topic of calibration. Okay. So, again, these are topics where I've quite a bit of material online. I'm just going to try to deal with the bare essentials to give us time, proper time for project work today and for the Java tutorials and so on. So forgive me for going fairly quickly through this. There's many types of sensitivity analysis that are relevant when it comes to models. And most of them we're not going to have a chance to look at here. But I'm going to concentrate on some of the most common, in general, what are the most common, and the ones best supported by the AnyLogic interface. Be aware there are things like structural sensitivity analyses where you examine modifying the model's structure and examining its impact on model output. Okay? What I'm going to be talking about today, though, is use of this particular model in order to examine the impact of stochastics, of uncertainty over time in the model on model results without varying any parameters on the one hand, and on the other hand, systematically varying certain parameters over a grid range, either one-dimensional or multi-dimensional, in order to capture variability in the results of the model that result from that. Now, we're going to be using a model that comes with AnyLogic for this. You will find other videos of me, most notably from 2 weeks ago, when my throat was in about this condition in North Carolina, and and we built a little model which had a parameter variation experiment from the ground up, or we extended it. I'm trying to remember if we built it from the ground up or extended it. In any case, we did something that was more extensive than we're going to be doing here. So you may want to look at that. I do have other videos of me building it from the ground up. So what I'm going to do is I'd like to run this model, this Monte Carlo TD. Well, actually, just double click on it first, and you'll see here that we could specify variations in parameter ranges. What I'd like to do is there's a bug in the AnyLogic interface here. Please, who can maintain the bug information? Could someone add this to the bugs? This is a known bug in AnyLogic we discovered in North Carolina. Basically, you have to double click on these things sometimes to get them to properly work. This is in AnyLogic 6. Look at that. It's switching sometimes without switching properly. It's doing it okay right now, but in general, you sometimes have to click on it, double click on it. Yeah, oh, look at that. Oh, that's evil. Okay. Okay. So click on freeform here, and you should see parameters just like this. Do you see that? Okay. Later, we're going to use freeform in order to draw from distributions for the parameters, but right now we're just going to run it. Now, what's going to happen is we're going to see you notice we're not changing any of the parameters. We're keeping all the parameters the same. These are the names of the parameters of the model. It automatically draws those in from our model. And we're going to run our model. And here, over time, we're going to see the results of many, many model runs in terms of the number of infectious people at a given point in time. So here it's running the model again and again and again and again. And it's darkening the square proportional to how many particular runs at a particular time interval yielded results that fell in a particular vertical interval in terms of the number of people infected, okay? So, for example, let's take time 20 here, okay? Take the period between time 20 and, I guess maybe 22. We could go look at it in Excel to verify. And maybe 22.5. So in this time period here, there were apparently many runs that had between 0 and perhaps 200 people here, and then there was no runs, essentially no runs that fell in this middle area, and then quite a few that had a larger number of people up here at the top, between about 5,000 and 7,000. And so you could imagine if you slice this through here, on a slice here, for this period of time, you'd see a sort of histogram that would be bimodal. It would sort of be high here, it would come down, it would be 0 for long periods of time, and then it would rise up, and then come back down up here. It's kind of this bimodal distribution. This results from running the models with the same set of parameters. But it's running it again and again and again with stochastics. Stochastics meaning there's uncertainty associated with it over time. Now, ladies and gentlemen, the model that we're looking at is none other than the model with which we started. The model which we started this boot camp. What may seem a long time ago, perhaps far away. You remember this model? Yeah, it was actually, this thing was colored gray in the one we saw, I think. But in any case, this model you'll recognize. Why are there stochastics in this model? Why are there stochastics? Why is there uncertainty? Even if given the same values of the parameters in main, why is there uncertainty?
Different starting positions?
Okay, actually, in each run, one person starts infective, so that doesn't differ much, but who starts infective, it differs. It infects a random person. Okay, in general, that will be the case. In this particular model, they're just, turns out they're transmitting to people across the entire space, but so there's no persistent number, but in general, it'll be their network will be random. That's right. What other features just in the natural history of progression? Good. This is a rate, and in fact, recovery is given by a rate. It's given by a chance per unit time. So sometimes for some people that occurs sooner and some later. Do you remember when we ran this initial model, we saw sort of a ragged edge? Do you remember that? A ragged edge to the expanding wave. Now that was with localized transmission. This one actually transmits globally. Oh gosh. Okay, so that leads to these kind of stochastic fringes around here. Ladies and gentlemen, I'd like you to right-click on this while we're in the theme of output and do copy all. And then I'd like you to go over to Excel, and I'd like you to create a new sheet, and I'd like you to paste. And this is what we'll see. We'll see this is now the data that was presented on that graph shown as counts. So there were, in time between 20 and 22.5, there were 8 samples where the model, the number of people, infected people within the model lay between 7,000 and 7,200. 5 where it lay between 6,800 and 7,000, etc. Okay? Okay, so here we have, we can explore, we can look at these counts shown graphically within the model output, also in a spreadsheet sense. But this data is indicating variability in model runs. Now, let me ask you this, ladies and gentlemen. How is it that this model was run many, many times? You'll notice that was part of the definition here. The definition was we're running the model 100 times as part of this. Who is responsible for running the model 100 times? The experiment. And so, in general, experiments have lifetimes that outlive main. For each of these 100 times, it was bringing main into existence. Main existed for a certain period of time while it was running, and it finished running, and this experiment salvaged some data from it, squirreled it away to present it, and then main was destroyed. And then main ran again and again and again. And if you want to see how this works, you can see here, this is actually a model I modified in North Carolina, sorry. You folks will only probably see one piece of this. If you scroll down in the parameter variation experiment, far down, after all these sort of checkboxes, you'll see this thing say before each experiment run. Do you see that? Do people see that? So what it's doing is it's clearing all the data that it's going to present in that 2D histogram. And then after each run of main, it's going to add in data, a data set that it got from main, added into that two-dimensional data set to present it on that graph. It's going to salvage the number of people infected over time from main and put it into the graph so it can be presented. This is what's going on, and this is going on after each run of the underlying main. This root here refers to main. It refers to the main class, and it's getting this data out just before that main class disappears, and it's putting it into this data infectious 2D, which is one of these types of data items you can add. If you go to main here, you'll find this if you go to the experiment, it lives in the experiment, this data infectious 2D here. And this data infectious 2D sets the appropriate information to display that on that graph. How many bins you want vertically and horizontally over time, etc. So that sets the kind of bins into which the data is accumulated. So when we count the number of, we count the number of times runs of the model have landed, have had a number of people infected between 7,000 and 7,200 that lie within, during the time 20 to 22.5. That's a result of of specifying these two things here. We have 40 horizontal intervals and 80 vertical, into which we use as bins to count the number of runs that fall into them.
Where is that section that you're looking at this?
It's in Monte Carlo 2D histogram experiment in this data, Infectious 2D. Yeah. Okay. Yeah. Okay. So, ladies and gentlemen, we've run this model again and again and again and again 100 times. Let's go there, and each time in the experiment, it is salvaging this information from the model on the number of infectious people over time and adding it in to be displayed in that big chart, adding it into this 2D histogram data set. And it makes sure that it counts the number of times it fell in certain categories. Any questions about that? Does that make sense? Yes, question, Ellen.
Quick question. I see how it's running 100 times when you click the button, but then on the parameter variation experiment, it says it's running 200 times. What's the relationship between the 200 and the 100?
Okay, so where is this?
So if you are just on the parameter, the Monte Carlo 2D histogram, just click on that.
Yeah.
And then you go down on the parameters, it says the number of runs is 200.
So, okay, I must be. I thought you said data infectious 2D.
Yeah, so just go into the Monte Carlo history and name.
Oh, this one. Okay, yeah.
You've got 100 runs.
Oh, I've got 200. Okay.
Yeah, I've got 200 as well, but it does stop.
Okay, I mean I could put 200 to be consistent. I was leading this in front of a boot camp 2 weeks ago, and maybe I changed it as part of that. Apologies. You'll notice while it's running it, incidentally, it's running it on both of my cores, both of my processing units available to this virtual machine down there. It's running them in parallel where possible. Okay. Okay. So here it's running it 200 times and accumulated across this. Okay, ladies and gentlemen, now I'd like to go and advance this further, though. Instead of just running it one time, I'd like to vary the parameters systematically. So I'd like to change it to be varied in range, and I'd like you to enter the following sets of parameters. So for average illness duration, make it a range. It can either be fixed or a range, and I'd like to enter it between 5 to 25 in steps of 5. Infection probability, by contrast, I'll make fixed at 0.8. Okay? Yeah. You have to make sure you double click on varied in range, because sometimes it doesn't listen as you click those buttons. So did someone record that bug? Okay. Priyasri and I encountered it in North Carolina too. Yeah. Okay. So make sure you double click on this thing. Okay. So it should be, these should be 1.0, 0.8, and 10,000 fixed. The top one should go from 5 to 25 in steps of 5. Okay? So ladies and gentlemen, how many different runs should this run? You'll notice it's grayed out here, number of runs. It should run 5 different runs right now. And we'll explore it with texture in just a minute. So now we're going to be running the model with different values of this parameter, average illness duration. Let's run it. Ready? Are you ready? Okay. Okay, there we go. It ran it 5 times. Hence it says 5 down here. Down in the lower left. 5. See that? And it ran it for 5 different values of that parameter. You can actually see them, right? Average illness duration As it stays longer, it requires more time to sort of drain the stock of people who are infectious. Speaking of, yes, uh-huh. I told it to just step these from 5 to 25, step 5, so it did 5, 10, 15, 20, 25.
Okay.
Indeed. Yeah. No, I can show you how to do that. We're going to do that next. You're exactly providing exactly the lead into my next question. So, ladies and gentlemen, Tiffany was perceptively asking, now, wait, it only ran 5 runs here, but there's stochastic variation within each run. Don't we want to capture that? Now that, ladies and gentlemen, for that, we will use a further feature. And this begins another nugget. So we're going to scroll down here, and you'll notice there's a thing that says use replications. Okay, use replications. And what that means is for each of those alternative parameter assumptions, we're going to be able to tell it to run it a certain number of times. Okay? We're going to be able to tell it run it, say, 10 times for each, or 100 times for each. We'll just do 10 to speed things up. But we could ask it to run it 100 times each for each of those alternative assumptions about average illness duration. Does that make sense? Should we run it? So how many times should it run now total? 50. There's 5 different alternative assumptions about average illness duration, and for each of those, we're going to be running it 10 times to capture the stochastics, the uncertainty attendant. Even with that alternative value, there's going to be some variation. And they lie before you. Does that make sense? You'll notice how many, it says it's run, 50 down here. The variability is notable, but please bear in mind that this graph does not capture the trajectories exactly. It may seem like it captures trajectories here, but just because there's a dark band all along the bottom doesn't necessarily mean any one run took that path. It could be that there were a bunch of late bloomer runs that went along here for a while and then took off, and a bunch of runs that came down early, and it contributes to a large number down here. It could have been there's some, and I will bet you there are some, but don't be fooled into thinking that you definitely have a sense of the individual trajectories by looking at this graph. This graph will show you the number that have fallen in here, but a given item here may be dark because some fell in while they were going up, some fell in that bin while they were coming down. You have to be a bit cautious about interpreting it. But, you know, it does give a sense of the wide amount of variation. You'll find that there is uncertainty, there is variability, but there's also regularity here. There's virtually none that fall in this upper region here. There's virtually none that fall in this region down here. There's some regularity behind this, some order behind this this variability. Okay, so here we are modifying a single parameter value, and I'd like, ladies and gentlemen, to now look at the effects of modifying several parameter values. So in addition to modifying average illness duration, I'd like you to modify infection probability such that it proceeds from 0 to 1 in a step of 0.1. So it's systematically, we're going to be varying both average illness duration on the one hand and infection probability on the other in a sort of grid of sorts. We're going to examine all possible combinations of those values. Does that make sense to people conceptually? Yeah? Okay. Okay, so I'd like you to run that. And now how many runs should there be? Can anyone tell me? I'll give you a hint. 0 to 1, step 0.1 will be 11 different. This is 5 different. So there'll be 550. 11 times 5 times 10 down here, the number of replications. Should there not? There should be. Okay? Okay, let's run this out. Now you'll notice something that's of significance, ladies and gentlemen. One talk I didn't have time to discuss in this boot camp, but which you'll find in my North Carolina boot camp, which was not an incubator, so I had some extra time, is a discussion of performance. A parameter variation experiment, ladies and gentlemen, will run your model absent a user interface for each run. For main is not lent a user interface here. You notice it's not displaying what is shown in main. And that's significant. It can save quite a bit of time, of computational burden, by not running that, by not showing those people moving around or whatever's in your user interface. So it actually can run your model much faster as a parameter variation experiment in some cases. So one of my first suggestions if people are dealing with a very slow model is, have you tried running it as a parameter variation experiment? That will give you some sense, is it a visualization type issue or is it an underlying model logic issue? This won't help speed up underlying model logic so much as visualization. And being able to tease those issues apart will help speed you on your way towards fixing the underlying problem. We're fortunate in that we have other tools like profilers, which you'll see me introducing in my recorded talks from North Carolina, which will also help us diagnose these things. Now here, ladies and gentlemen, we see, probably if you're running on your screen, you'll probably see this more clearly than you do in the screen here. There's a slight thin patina up in this area here. A very slight kind of graying, but most of the runs lie down here, it seems, on this x-axis. And why? Because they don't take off. The combination of parameter values is such that it maybe never takes off, or it takes off very late. This upper area is hit by a small number of different runs. And if we were to export this by right-clicking, choosing Copy All, and putting it into Excel, we could see how many fall there. But it's a small number compared to the number that fall down here. Okay? Does that make sense? Okay. Okay. So, ladies and gentlemen, we've seen a bunch here, and I just want to highlight a few higher-level points. I have quite a lot of slides which discuss extra implications, which suggest ways to decrease the number of combinations you need, things like Latin squares, orthogonal arrays, judiciously selecting combinations of parameter values, because each successive parameter you want to vary adds another whole burden. And through use of techniques from as varied as dimensional analysis to orthogonal arrays, you can actually get a lot of horsepower with doing fewer combinations of parameter values. I don't have time to go into that here, although I'll be happy to answer questions about it on an ad hoc basis. However, I want to draw out a few high-level points. The first point is a very important conceptual point about how any logic works, which is that the experiments are conceptually distinct in terms of their lifetimes from the main class. A given one of these experiments may run the main class many times over. And that's important. It's important if you want to run parameter variation. As we'll see, it's important for calibration. But ladies and gentlemen, it's also important if you want to do 2 runs of a model and compare their results. If you want to do one run that's a baseline, one run that's an alternative with the same set of basic other parameter settings, just differing, say, in one setting, and you want to compare the gain of the intervention from the baseline, you could use a parameter variation to run it twice, for example. Parameter variation experiment to work, in terms of the underlying plumbing of it, it reads out values from the main class, squirrels them away in places that it can present them. And in my particular case, we modified it in North Carolina so that over here on the right-hand side, it will show a little histogram of the number of times different numbers of infected people at the end of the simulation fall within different categories. And you'll find videos of me presenting on that, okay? So parameter variation experiments rescue information. They salvage information from main, which is about to be destroyed, in a way that can allow you to present it or output it as data. Over many, many runs of the model, particular runs, it can extract and accumulate data to allow you to export it. And I'd be happy to sort of talk more about that, but especially to refer you to those videos where I cover that in more detail. Okay? So those are a couple of high-level features. Parameter variation is one of those things that if you want to publish a model these days, an A-based model, this is viewed as being a very important thing to be sure to include in your model. Reviewers will very typically ask to see some evidence that you've done a parameter variation experiment. Yes?
Actually, this is a question I'm taking this afternoon, which is,
yeah.
is there a guide or something published with the current evolution best practices for publishing a model?
Yes, there are. Yep. Yeah, I could send you a reference on this, yeah. So they're from certain sub-areas of the modeling community, but they would be germane to across multiple modeling areas. So yeah, I could give you some suggestions on that. Yeah. Okay, so ladies and gentlemen, that was parameter variation. I now want to very briefly talk about calibration. Oops. Calibration, fortunately, we're going to be able to talk about with this same model.